This is section 6.4, and we're going to talk a little bit more about graphing rational functions. We've already taken a look at how to draw a graph if we're just shifting a basic rational function like 1 over x, moving it left or right, up or down, reflecting it, those kinds of things. But what about more complicated rational functions, ones that don't follow just a shift of that basic graph? We've already seen enough to know that our rational function graph is very much shaped by its asymptotes. So if we could figure out the asymptotes, that goes a long way to helping us recognize what the graph's going to look like. We'll concentrate mostly in this section about learning to find those asymptotes by hand. The other two things which can be useful and which we already know how to find are x-intercepts, which we can find by letting our y value, or f of x, equal 0. And then the y-intercept, which we can find by letting x equal 0. Once we've identified these three things, intercepts, x and y intercepts, we'll be able to, asymptotes and x and y intercepts, we'll be able to then fill in things that we can't quite get yet by hand using technology. So let's talk about those asymptotes. There are three different kinds. The first is the vertical asymptotes, and those we've seen a bit and probably already understand to a large extent. Those occur when the function is undefined, which of course happens when the denominator is 0. So vertical asymptotes occur at x values where f of x is undefined. So in other words, at x values that make our denominator, q of x, equal to 0. The other two types of asymptotes, one we've seen, one not so much yet, all have to do with the degrees of p and q and how they relate to one another. If the degree of the numerator, p, is larger than the degree of q, we get what's called a slant asymptote. And the way to find that slant asymptote is by the long division. So we find this by dividing q of x into p of x. Our slant asymptote is just the quotient. We can ignore any remainder. The other possibility is that we've got a horizontal asymptote, and there's actually two ways that that might happen. One is if the degree of the numerator is equal to the degree of the denominator. In that case, we get a horizontal asymptote, which we can find by taking the ratio of the leading coefficients. So our horizontal asymptote is y equals the ratio of the leading coefficients. We'll look at examples of that. If you're not quite sure what that means yet, we'll look at an example and I think it will become a little bit more clear. The final possibility is that the degree of the top, p, is actually smaller than the degree on the bottom, the q. We still get a horizontal asymptote, but in that case, it's always y equals 0, the x-axis. Right, so that's kind of our outline of how to find asymptotes, and we'll look at several examples so you get to see exactly how each one of those works. All right, in my first example, I've got the function x plus 1 over 5x squared plus x minus 6. And we're asked to find the intercepts and the asymptotes by hand, and then sketch our graph using the calculator or Desmos to help us a little bit to fill in the details that we won't yet be able to figure out by hand. It actually takes some calculus before we can actually figure out everything we would need to draw a full graph here. All right, so let's start with, I'm going to start with my intercepts. The x-intercepts we find by letting y equal 0. So my equation becomes 0 equals x plus 1 over 5x squared plus x minus 6. In the very last section, we talked about how to solve those kinds of equations. We just want to clear the fraction by multiplying both sides by the denominator. So I'll multiply both sides by 5x squared plus x minus 6. On the left-hand side, since we're multiplying by 0, we still have 0. And on the right-hand side, I can divide those out, meaning I'm left with just x plus 1. And that means x is negative 1. Or in other words, my y-intercept is negative 1, 0. I can go ahead and put that on my graph right now. There we go, there's our x-intercept. Let's do the y-intercept as well. For the y-intercept, we plug in x equals 0. So y would be 0 plus 1 over 5 times 0 squared plus 0 minus 6. And that's just going to give me negative 1/6. So my y-intercept is 0, negative 1/6. And that'll be just below the origin here, about there. All right, so x and y-intercept are graphed. Let's talk next about our asymptotes. Vertical asymptote first, or asymptotes. Those occur any place that the function is undefined, or in other words, any place where the denominator is equal to 0. Typical here, we're just going to talk about p being the numerator and q being the denominator. So the vertical asymptote will always be where the denominator, where q of x equals 0. So in this case, that would be 5x squared plus x minus 6 equals 0. And I'm going to try to factor that. It's a trinomial, so I'm going with sum and product. Sum of 1, product of negative 30. So let's see, 5 and 6, and we'll let that 5 be negative. That should do it. So I'm going to rewrite this as 5x squared minus 5x plus 6x minus 6. Let's see, I can factor out a 5x, which gives me x minus 1, plus 6 times x minus 1 as well. So I have x minus 1 times 5x plus 6 equals 0. If x minus 1 is 0, that gives me x equals 1. And if 5x plus 6 equals 0, let's see, I would have negative 6 divided by 5. Those are my vertical asymptotes. I'm going to go ahead and put those on the graph right now as well. X equals 1 would be here. And x equals negative 6/5, just a little bit past negative 1 here. About there. All right. One more thing to find, and this is the last thing. This depends on the degrees of P and Q. So in this case, I'll notice the degree of P is 1, and the degree of Q is 2. So the degree of P is smaller than the degree of Q. So here we go. Degree P is smaller than degree Q. Tells me I have a horizontal asymptote, specifically y equals 0 or the x-axis. So degree P less than degree Q. Degree P here was 1, degree Q was 2. Tells me my horizontal asymptote is y equals 0. Okay. There's not a lot of actual work to show here, so I'm just sort of justifying it, explaining to anyone who might read this why I concluded that. All right, so let's draw that one in as well. All right. You may get to the point where you can guess a little bit more what these look like, but for now, I think we're at the stage where we can probably done everything we can by hand. And I'm going to go ahead and say I've got kind of my framework here. I'm going to use Desmos now to help me fill in the rest. So let's go ahead and put our function here into Desmos. There we go. And I'm actually going to spread that out just a little bit more. That's not too bad. All right, you can essentially see what's going on here. The y-axis is really huge. Let's make that a little bit. There we go. That's a little bit better. I can sort of see the shape of it a little bit better if I don't have quite such large values on my y-axis. I already know what my vertical and horizontal asymptotes are, so just to help me see them, I'm going to graph those as well. You've seen before that if we graph them as dotted lines, it kind of helps us to recognize that framework that we've built. We know that x equals 1 is one of our vertical asymptotes. X equals negative 6/5 was another. And our horizontal asymptote was y equals 0. So adding those asymptotes just kind of helps me see the framework. Notice there's that x-intercept that we found at negative 1. There's the y-intercept right there at negative 1/6 or negative 0.167. So all of the things that we found by hand are recognizable, and I can now just use that graph to sketch in the rest of my function. So I'm looking at this and drawing at the same time. The left side, my end behavior is really close to the asymptote, and then it comes down along the vertical asymptote. Got that sort of a little wave shape in between the two asymptotes. And then the right-hand side goes up along the vertical asymptote. It comes down and approaches the horizontal asymptote. So my picture by hand now looks like that. I'll list the asymptotes, x equals 1 and x equals negative 6/5, my horizontal ones, and y equals 0, which was my vertical one. As far as the domain, we know that the domain has to omit the vertical asymptotes. And so we know x cannot equal 1 and x cannot equal negative 6/5. The range, in this case, looks like the range goes all the way from negative infinity to infinity. Notice that even though we've got a horizontal asymptote here at 0, we did have an x-intercept, so y does equal the 0 at some point. So negative infinity to infinity here. I'm going to add one more thing. Let's talk about the end behavior here. This graph approaches y equals 0 on the left, and it also approaches y equals 0 on the right. All right, let's take a look at another one. All right, here we go. 2x squared over x squared plus 2x minus 8. Once again, I'm going to start with my intercepts. So for my x-intercepts, I substitute y, or in other words, f of x equals 0. And we're going to clear those fractions. You've seen this a bunch of times now. Multiply both sides by the denominator. So we just end up with 0 equals 2x squared, which just tells me x is 0. So my x-intercept is the origin, 0, 0. And of course, I can already see that that 0, 0 is also on the y-axis, so I'm expecting the same thing for the y-intercept. But let's go ahead and do the math just to show it. If I plug in 0 for x, I do get 0 divided by negative 8, which is 0. So in this case, the x-intercept and y-intercept are actually the same. All right, let's look for vertical asymptotes next. Vertical asymptotes are the ones that occur when the function is undefined, or in other words, when q of x equals 0. Again, just a reminder, we typically think of the top as being P and the bottom as being Q. So my vertical asymptotes in this case are going to happen when x squared plus 2x minus 8 is equal to 0. Once again, I've got a trinomial. I'm going to try to factor here. So I'm going to go with a sum of 2, product negative 8. So I'm thinking 2 and 4, with the 2 being negative. And this time I've only got a 1x squared, so I can use the shortcut. X squared has to be x times x. So I'll have x minus 2 and x plus 4. If x minus 2 is 0, I get my first vertical asymptote, x equals 2. And if x plus 4 is 0, my other vertical asymptote will be x equal negative 4. So I'm going to go ahead and put those on my graph as well. X equals 2. And x equals negative 4. All right. Looking at the degrees of P and Q, they're the same, right? They're both second degree. So that tells me, again, I'm going to have a horizontal asymptote. The degree of P, which is 2, is equal to the degree of Q, also 2. So my horizontal asymptote is going to be y equals, and when the degrees are equal, y is the ratio of the leading coefficients. What exactly does that mean? Well, my leading coefficients are just the coefficients of the highest powered terms, right? So leading coefficient on the top, the leading coefficient of P would be 2, and the leading coefficient of Q is actually 1. It's not really written there, but we all know that's really a 1. So I just take the ratio, 2 over 1. Or in other words, y equals 2. All right, let's put that one in as well. All right, so again, we've got our structure, right? We've got our asymptotes, which give our graph structure. We have just one intercept this time at the origin. That's really as much as I can do by hand. So I'm going to go ahead and put this into Desmos to figure out how the rest of the graph is going to look. All right, and again, I'm going to add the asymptotes just to help me sort of see how the structure is working around those asymptotes. Vertical asymptotes were x equals 2 and x equals negative 4. And then the horizontal asymptote was y equals 2. All right, and then you can see left side is just kind of up in that corner. Again, I'm going to kind of draw as I go. In between the asymptotes, we have kind of, almost looks like sort of a lopsided parabola looking shape. Again, I'm just going to draw that in there. And then there's something sort of interesting that happens over here on the right. We can see the graph going up and approaching the vertical asymptote here, but then it crosses through the horizontal asymptote. Graphs can never cross a vertical asymptote. Vertical asymptotes are where the function's undefined. They can cross horizontal asymptotes. Horizontal asymptotes are all about end behavior. So notice here the graph has crossed the horizontal asymptote, but if I come out here, you can just start to sort of see that it comes down for just a little while and then it starts to slowly go back up again and approach the horizontal asymptote as we go out further. So I'm going to kind of try to draw that as well. Up near the vertical asymptote, crosses the horizontal, looks like at about x equal 4. Goes slightly below it, and then comes up close to it, again in the long run. So my picture now looks like this. My asymptotes, x equals 2 and x equals negative 4, the vertical asymptotes. And then the, let's see, y equals 2, the horizontal asymptote. By the way, I don't know why, but I just had a flashback to the last problem. I think I labeled them wrong, that one. Sorry about that. I did. X equals 1 and x equals negative 6/5 are vertical asymptotes, right? Sorry about that. And then the y equals 0 is the horizontal. Apologize for that. But on this graph, I think I got it right here. Negative 4 and x equals positive 2, those are vertical. And then y equals positive 2 is the horizontal. All right, my domain, x cannot be negative 4, and x cannot be 2. Again, that's sort of an abbreviation of the domain, but it's understandable for anybody who would read this. And the range, once again, I'm going to say that to some extent we can cross that horizontal asymptote, but there's going to be a little gap in here, right? Let's see. Let's start with our negative infinity to 0. This section in here goes from negative infinity to 0. And then from whatever the smallest y value is in here up to positive infinity. I'm going to have to go back to Desmos to find that. It helps me identify it if I kind of click in the general neighborhood. Looks like the smallest y value there is about 1.778. And the graph certainly goes up to infinity from there. All right, and then let's add just a quick statement about end behavior again. This graph approaches y equals 2 on the left, and it also approaches y equals 2 on the right. As far as this class is concerned, if you have a horizontal asymptote, it'll always just be one horizontal asymptote going all the way across, so we'll always have this identical end behavior on left and right. But if you go on and take some more math classes, you'll find out that some graphs have different horizontal asymptotes on the left and right side. So preview of coming attractions there. All right, we have one more. And I'm going to start once again with my intercepts. For the x-intercepts, I want to set the y equal to 0, or the f of x equal to 0. And when I multiply both sides by the denominator to clear fractions, I get 0 equals just that cubic polynomial. All right. Well, looking at that, I'm going to say that I don't think it's 4 terms, but I don't think grouping is going to work. If I factored out x squared here, I'd get x plus 2, and that's certainly not going to turn into an x plus 2 over there. So I can't factor this. I could try that rational zeros theorem, or I could use technology. And I'm going to say, considering all the other stuff that we're doing here, I'm going to say, let's just go ahead and say we'll use technology when we eventually graph this by hand, or, well, excuse me, when we eventually graph this on Desmos, we'll just go ahead and use technology this time, since it wasn't much of an easy matter to get the x-intercepts by hand. All right, let's try the y-intercept, setting x equal to 0. And everything becomes 0 except the 1 and the negative 4. So y would be negative 1/4. And there is my y-intercept. I'm just going to quick plot that on my graph. All right, we're ready to talk about asymptotes. As far as any vertical asymptotes, if I once again think of my numerator as p and my denominator as q, vertical asymptotes occur when the denominator, when q of x is 0. So in this case, when x squared minus 4 is 0, that says x squared equals 4, so x would be plus or minus 2. Let me add those to my graph. X equals negative 2, and x equals positive 2. And there's that y-intercept. All right. In this case, when I look at my degrees, notice the degree of p is larger than the degree of q. And so this is the case where I have the slant asymptote. Degree p bigger than degree q. And I'm supposed to find the slant asymptote by doing the division. So we'll have a slant asymptote this time, because the degree of p, which is 3, is larger than the degree of q, which was 2. Technically speaking, we really only get a slant asymptote when the degree of p is exactly 1 more than the degree of q, but for the purposes of this class, those are the only cases you'll see. All right, so I have to find this by doing my division. We haven't talked about that for a minute here, so let's review that a little bit. I start by looking at just the first terms. X cubed divided by x squared would be x to the first. And then I'm going to multiply. X times x squared is x cubed. X times negative 4 is negative 4x. And notice when I write them, I'm lining them up underneath their like terms. I'm going to subtract those, which is going to make that negative, and it'll make the negative a positive, right? Minus a negative. So my x cubes subtract to 0. I have a 2x squared minus 1x and the plus 1. Let's divide again. 2x squared divided by x squared would be a positive 2. And then I'm going to multiply. 2 times x squared. 2 times negative 4 would be negative 8. Once again, I'm going to subtract, making that negative and that positive. And I end up with a minus x plus 9. That's now my remainder, since x divided by x squared would be fractional. So when I'm finding a slant asymptote, I simply ignore my remainder. And my slant asymptote is the quotient. Y equals x plus 2. All right, I'm going to add that to the graph. So y equals x plus 2, that's a line with a y-intercept at 2. And the slope here is 1, right? So I could go up 1 and over 1, up 1 and over 1. So there's my slant asymptote. Y equals x plus 2. All right, again, the asymptotes become sort of the structure or framework that I build my graph around. So let's go ahead now and get the rest of it with Desmos, and then we'll sketch in what we see. And let's see, I might want to see a little bit more here. There we go. And let's add our asymptotes. Verticals at x equal negative 2 and at x equal positive 2. And then the slant asymptote, y equals x plus 2. All right, the vertical asymptote is pretty familiar to us, right? That behavior here where the graph goes sort of down along the vertical asymptotes on this side and up in here. But look at the slant asymptote. Do you see how the graph is on the left side getting really close to this part of the slant asymptote? And on the right side it's getting very close to that part of the slant asymptote. So I'm going to sketch in what I see near the slant asymptote down on the left. Oh, and you know what? I forgot. We didn't get our x-intercepts by hand this time, so let me just go ahead and let Desmos help me with that. About negative 3.5 is my x-intercept over here on the left side. And then that, again, sort of a lopsided parabola shape. Whoops. I had the y-intercept at -1/4. I have an x-intercept at about 0.2 and another one at about 1.3. And I'll draw that sort of a lopsided parabola shape. And then over on the right-hand side, I've got that near the vertical asymptote and then finishing up near the slant asymptote. So there's my sketch of what I saw using Desmos. Vertical asymptotes at x equal -2 and x equal +2. A slant asymptote y equals x plus 2. As far as the domain, can't touch the vertical asymptotes, so x is not equal to -2 and x is not equal to +2. And my range this time looks like -infinity to infinity. You can actually see it right over here on the left. This is going to keep going to the left and down toward +infinity, and then it goes all the way up and positive here. So it's going to cover everything from -infinity to infinity. And as far as the end behavior, because of the way the slant asymptotes work this time, this one really is just going to go down to the left. And this side is going to go up to the right, which is usually sufficient. Although if you want to be more specific, you could say this happens along the line y equals x plus 2. But I would be fine with just saying down to the left and up to the right in a case like this. All right, so that brings us to the end of 6.4. Again, the biggest thing here is learning to identify those asymptotes by hand. You will still need technology to help you fill in the details of this graph.